Imagine a cosmic visitor traveling billions of years across the void of space, carrying with it a chemical toolkit older than our Sun, a toolkit that helps spark life on Earth but without being alive itself. This is 3I Atlas, an interstellar object whose latest observations are rewriting what we know about comets, molecular chemistry, and the early ingredients of life. Among the many extraordinary findings, one stands out. 8% of the vapor released by 3I Atlas is methanol. To put that in perspective, comets from our own solar system typically have about 2%. In other words, this object carries 4 times more methanol proportionally than anything we've ever studied nearby. That's a staggering enrichment for a molecule that scientists consider essential for complex chemistry, a precursor to amino acids, sugars, and even the building blocks of DNA and RNA. Methanol isn't just interesting, it is a cornerstone of chemical complexity, a stepping stone on the path toward life itself. Alongside methanol, observations from ALMA, the Atacama Large Millimeter, Submillimeter Array, detected hydrogen cyanide, one of the most versatile molecules needed to form amino acids. In 3I Atlas, the ratio of methanol to hydrogen cyanide is among the highest ever measured in any comet, interstellar or local. Other instruments added to the story. Spherix detected methane and cyanide, as well as a dramatic post-perihelion brightness surge, while Webb found CO2 unusually elevated above solar system trends, alongside methane deep inside. Swift measured water being released at 40 kilograms per second from distances where such rates make no simple sense. Even the South African radio telescope, Meerkat, detected hydroxyl absorption lines, confirming water's presence. Each instrument, each observation, builds a convergent, unprecedented picture of an interstellar traveler unlike anything studied before. These findings prompted Avi Loeb, who has long speculated on the origins of 3I Atlas, to describe it not as a threat, but as a friendly interstellar gardener. A gardener, he said, depositing molecules that could seed life rather than carrying life itself. Today, we'll walk through every molecule detected, explain what it does, why its concentrations are unusual, and what this evidence does and does not mean for ideas like panspermia, the hypothesis that life or its building blocks can travel between star systems. We'll explore how a 7 billion-year-old object from another star system carries the exact molecular toolkit that preceded life on Earth, and why the distinction between molecules and life is critical. By the end, you'll understand the extraordinary implications of this cosmic delivery system. But first, we need to understand the data itself. The primary detections of methanol and hydrogen cyanide came from ALMA, one of the most sensitive radio observatories ever built. Martin Cordner of NASA's Goddard Space Flight Center led the team that observed 3I Atlas multiple times between August and October 2025. These detections were unambiguous. Both molecules came from the object's rocky core, with methanol also present in significant concentrations throughout its coma. Product beyond ALMA, NASA's Spherix mission added another layer to the story, observing 3I Atlas in both August and December 2025. Spherix captured a dramatic post-perihelion brightening roughly 2 months after the comet's closest approach to the Sun on October 29. This wasn't a gradual warming, it was an eruption. Volatiles buried deep inside the comet, insulated during its approach, absorbed the delayed thermal wave from the Sun and suddenly released, exposing interior molecules that had remained locked away for billions of years. Methanol, hydrogen cyanide, and methane all surged from these subsurface reservoirs, giving scientists a rare glimpse into the untouched chemistry of a planet-forming system predating our sun. What Spherex witnessed wasn't just surface activity, it was 3I, Atlas revealing its ancient inner workings for the first time. Webb Observatory contributed further, detecting elevated CO2 levels, carbon monoxide, water, and carbonyl sulfide, along with methane and nickel vapor in August 2025. SWIFT confirmed the presence of hydroxyl, the ultraviolet signature of water, at astonishing rates. Meanwhile, Meerkat in South Africa recorded 2 distinct hydroxyl absorption lines, marking the first radio detection of an interstellar comet and confirming the water inventory observed by other instruments. Each observation, made with different instruments, using diverse techniques, reinforced the same conclusion. This is the most comprehensive molecular characterization ever performed for an object from beyond our solar system. It's a convergence of evidence, a mosaic of measurements painting a clear picture of a chemical time capsule traveling through our cosmic neighborhood. So why is methanol generating so much attention? Methanol, CH3OH, is chemically simple, yet it plays an outsized role in prebiotic chemistry. In laboratory conditions, it leads to formaldehyde, which can polymerize into sugars such as ribose, the backbone of RNA, the molecule many origin of life researchers believe was the first self-replicating system. Methanol also feeds into amino acid production through the Strecker synthesis, which requires simple precursors, including cyanide compounds. Amino acids are the building blocks of proteins, the workhorses of all biochemistry. NASA astrochemist Martin Cordner notes that high chemical complexity is nearly impossible without methanol. In solar system comets, methanol typically accounts for roughly 2% of the volatile fraction. In 3I, Atlas, it's 8%, a dramatic enrichment that signals a markedly different formation environment than anything in our solar system. Hydrogen cyanide, HCN, tells a complementary story. Infamous for its lethal toxicity on Earth, it paradoxically serves as a critical molecule in prebiotic chemistry. HCN reacts with water to form adenine, one of the nucleobases in DNA and RNA, and participates in amino acid formation alongside methanol. The methanol to HCN ratio in 3I, Atlas, is unusually high, suggesting a chemistry that favors complex organic synthesis rather than simple toxicity. Avi Loeb highlighted this ratio when interpreting the ALMA findings, framing 3I, Atlas as a friendly interstellar gardener seeding prebiotic chemistry rather than carrying life itself. Whether natural or artificially engineered, this chemical balance favors molecular growth over harm, a nuance that makes the object extraordinary from a scientific perspective. This post-perihelion eruption, combined with the observed molecular abundances, allows scientists to see the interior of a 7 billion-year-old object formed long before our sun existed. Methanol, HCN, methane, CO2, water, all released intact after eons traveling through interstellar space. The interior chemistry survived cosmic rays, extreme cold, and the vast emptiness of the galaxy, giving humanity a direct window into molecular processes from another star system. Now that we've explored what was detected and how, the next question is what these molecules actually tell us about 3I, Atlas, and its origins. This is where panspermia, the idea that life or its building blocks can travel between star systems, enters the discussion. It's important to separate fact from speculation. Weak or molecular, panspermia suggests only that the chemical precursors of life, organic molecules like methanol and hydrogen cyanide, can survive interstellar journeys. Strong panspermia goes further, claiming that living organisms could survive such a trip and seed life elsewhere, a much more demanding scenario. Then there's directed panspermia, proposed by Francis Crick and Leslie Orgel in 1973, suggesting deliberate delivery of life by intelligent civilizations. What the 3I Atlas data confirms is consistent with weak panspermia. The molecules themselves, not life, survive. This distinction is subtle but crucial. 3I Atlas isn't alive, and its molecules didn't come from life. They are prebiotic, forming through natural cold chemistry in a protostellar disk billions of years ago, entirely independent of biology. The concentrations of these molecules are just as revealing as their mere presence. Methanol, at 8% of the volatile fraction, is 4 times higher than what we observe in solar system comets. While the methanol to HCN ratio ranks among the highest ever measured, CO2 is 4.5 sigma above the solar system trend, methane hides deep in the interior, and even the nickel to iron ratio is elevated. Each of these measurements tells the same story. 3I Atlas formed in a colder, more carbon-rich environment than our solar system. The CO2 and methanol ice lines in its parent protostellar disk condensed at smaller distances than ours, suggesting a thermal structure very different from the solar nebula. Its home system was richer in organic molecules relative to water, whereas our disk was water-dominated. Elevated nickel-to-iron ratios also point to formation around a star in a less metal-rich environment, consistent with older stars or stars in the outer galaxy. Current estimates place 3I Atlas's age at roughly 7 billion years, meaning it formed 2.4 billion years before our Sun in a chemically younger, dynamically different galaxy. This isn't just a fingerprint of a planetary system, it's a snapshot of the galaxy itself, a chemical record of how the universe processed elements and molecules billions of years ago. By studying 3I Atlas, we're not only seeing what another star system produced, we're glimpsing chemistry from an era when star formation, elemental abundances, and molecular distributions were markedly different from today. The unusually high methanol content is particularly telling, hinting at a formation environment far colder than what we find in the solar neighborhood. Methanol forms efficiently on icy grain surfaces when carbon monoxide reacts with hydrogen under cold conditions, a process known as hydrogenation. The elevated CO2 levels already suggested a colder birthplace. The methanol enrichment confirms it. 3I Atlas is a chemical fossil, carrying intact the molecular record of its home system across billions of years of interstellar travel. The broader implication raises an even bigger question: how common is this chemistry? Astronomers estimate that at least one 3I Atlas-sized interstellar object exists within 4.5 astronomical units of the Sun at any given time. This is based on detection rates from surveys like those that found Oumuamua, Borisov, and now 3I Atlas. As instruments improve, particularly with the Vera Rubin Observatory's LSST, the number of detected interstellar objects is expected to rise dramatically. If 3I Atlas's chemistry is typical rather than exceptional, it suggests a continuous influx of prebiotic molecules into our solar system. Every planet, past and present, could be receiving a background shower of organic material, some of it capable of contributing to the early chemistry that leads toward life. Early Earth, during the heavy bombardment period 4.1 to 3.8 billion years ago, likely received similar deliveries, a combination of local and interstellar material. Let's dive deeper into why methanol and hydrogen cyanide are so critical to understanding 3I Atlas and prebiotic chemistry. Methanol may seem simple, just one carbon atom bonded to a hydroxyl group, but its role in molecular evolution is extraordinary. In laboratory experiments, methanol can be converted into formaldehyde, which then polymerizes into sugars like ribose, the backbone of RNA. RNA is widely regarded as one of the first self-replicating molecules in Earth's early history, making methanol an essential stepping stone toward life. Methanol also contributes to amino acid production through the Strecker synthesis, where simple precursors like cyanide and ammonia react to form amino acids, the building blocks of proteins. Proteins, in turn, drive the chemistry of life, acting as enzymes, structural elements, and signaling molecules. Without methanol, these pathways toward complexity would be far less efficient, or in some cases, chemically implausible. Martin Cordner puts it bluntly, very high chemical complexity is nearly impossible without methanol, making 3I, Atlas's 8% abundance, remarkable. Hydrogen cyanide, HCN, adds another layer to the story. It is notoriously toxic to life today, yet in prebiotic chemistry it is foundational. HCN reacts with itself and water to produce adenine, one of the 4 nucleobases of DNA and RNA, first demonstrated in experiments by Juan Oro in 1961. HCN also participates in the same Strecker pathway as methanol, linking these molecules in a delicate chemical balance. The unusually high methanol to HCN ratio in 3I, Atlas suggests a chemistry favoring organic synthesis over simple toxicity. Avi Loeb referred to this balance when he called 3I, Atlas, a friendly interstellar gardener, emphasizing the delivery of molecular seeds rather than life itself. It's a precise metaphor. The comet doesn't carry organisms. It carries the ingredients, the molecular soil, from which life could, under the right conditions, grow. Observations of 3I, Atlas, during its post-perihelion eruption further reveal the inner workings of this ancient object. Spherex caught the dramatic brightening in December 2025, when the comet had already passed its closest approach to the Sunday. Heat from the sun took weeks to penetrate deeper layers, triggering the release of volatile compounds from the interior. Methanol, HCN, methane, and CO2 surged outward, giving us an unprecedented look at material that had remained intact for 7 billion years. These molecules were not surface contaminants. They were primordial, formed in a protostellar disk, predating our Sunday. This event effectively opened a window into a chemical world far older than our solar system, allowing scientists to study intact prebiotic chemistry that has traveled across interstellar space unaltered. The elevated concentrations in 3I, Atlas also tell a story about its birthplace. Methanol and CO2 abundances, along with the presence of methane in the deep interior, indicate formation in a cold, carbon-rich protostellar disk. In such environments, CO reacts efficiently with hydrogen to form methanol on icy grains, a process that requires extremely low temperatures. The elevated nickel-to-iron ratio hints at formation around a star in a less metal-rich environment, consistent with older stars or stars in the outer regions of the galaxy. 3I, Atlas likely formed 2.4 billion years before our Sun, in a galaxy chemically younger than today, making it a time capsule of both molecular and galactic evolution. Taken together, these molecular fingerprints confirm that 3I, Atlas carries prebiotic chemistry across interstellar space, intact and releasable. Every detection, methanol, HCN, methane, CO2, water, nickel vapor, paints a consistent picture of a chemically rich, cold, and ancient origin. The data demonstrates that the universe produces the molecular toolkit necessary for life in multiple star systems, and that these molecules can survive billions of years traveling between stars. It's not life itself, but the essential ingredients, the seeds of chemistry that set the stage for life where conditions allow. Comparing 3I, Atlas to comets within our own solar system highlights just how extraordinary this interstellar visitor is. In our neighborhood, comets typically have methanol making up around 2% of their volatile content, while hydrogen cyanide levels are more moderate. In contrast, 3I, Atlas shows methanol at 8%, 4 times higher, and a methanol to HCN ratio among the highest ever recorded. CO2 is 4.5 sigma above solar system trends, methane hides in its deep interior, and even the nickel-to-iron ratio exceeds what we normally see. Each of these measurements tells a consistent story. 3I Atlas formed in a colder, more carbon-rich environment than anything in our solar system. The ice lines for CO2 and methanol condensed closer to its star. The disk was chemically richer in carbon-bearing molecules relative to water, and the metallicity points to an older star, possibly from the outer galaxy. In short, 3I Atlas carries a chemical fingerprint of a planetary system fundamentally different from ours, formed 2.4 billion years before our Sun, and revealing how chemistry in the galaxy has evolved over time. This opens a profound question. How common is this chemistry across the Milky Way? Based on detection rates from objects like Oumuamua, Borisov, and now 3I Atlas, astronomers estimate at least one 3I Atlas-sized interstellar object exists within 4.5 astronomical units of the Sun at any given time. The Vera Rubin Observatory's LSST will dramatically increase these detections, suggesting that prebiotic organic chemistry may be constantly flowing through our solar system. Some molecules fall to planetary surfaces, some are absorbed by the Sun, and some continue their journey outward. Early Earth, during the heavy bombardment period between 4.1 and 3.8 billion years ago, would have received a mix of local and interstellar material, delivering not just water and minerals, but prebiotic chemistry like methanol at 4 times solar system levels, hydrogen, cyanide, and other organic molecules crucial for the origins of life. 3I Atlas is far from unique. It represents a population that has been delivering chemistry to our solar system for billions of years. Understanding what this actually means requires clarity. The detections do not indicate life on 3I Atlas. No organisms, metabolic activity, or biological processes have been observed. The molecules are prebiotic, not biological. They did not come from a living system. The data also does not confirm strong or directed panspermia. It only demonstrates weak panspermia is possible, meaning the chemical building blocks for life can survive interstellar travel. Yet this is still extraordinary. The chemistry of 3I Atlas is intact after 7 billion years, enduring cosmic rays, extreme cold, and interstellar voids, and remains chemically active once warmed. It shows that the delivery of prebiotic molecules between star systems is not just theoretical, it has occurred, and it can be measured. This leads to a fundamental takeaway. The universe produces the ingredients for life in multiple star systems, and these ingredients are robust enough to survive the harshest conditions of interstellar travel. Early planets, like Earth, may have benefited from a continuous supply of these molecular seeds. While we cannot claim that 3I Atlas's chemistry sparked life anywhere, it moves the discussion from theoretical possibility to empirical reality. We are witnessing the first direct evidence that prebiotic chemistry can travel intact across billions of years and light years, arriving ready to participate in chemistry under suitable planetary conditions. The friendly interstellar gardener metaphor Loeb uses is strikingly apt. It's not delivering life, but the molecular seeds, the toolkit that make life possible if the environment allows. As we reach the conclusion of 3I, Atlas's story, it's essential to summarize what these molecular detections truly mean and what they do not. 3I. Atlas does not carry life. No biological activity, no organisms, no metabolism has been observed. What it carries is prebiotic chemistry, methanol, hydrogen cyanide, methane, CO2, water, and other molecules that form the chemical foundation for life. These molecules were produced through entirely natural processes in a protostellar disk billions of years ago. They are ancient, frozen in place for 7 billion years, and have now been released intact as the comet approached and then receded from the sunday. This is the chemistry that, on early Earth, preceded the emergence of life, delivered not by chance, but as part of a cosmic population of interstellar objects continually passing through our solar system. The significance of the concentrations cannot be overstated. Methanol at 8% of the volatile fraction, 4 times the solar system average, combined with an unusually high methanol to HCN ratio, and CO2 and methane anomalies, all point to a parent system that was colder, more carbon-rich, and older than our own solar system. The elevated nickel-to-iron ratio also reflects formation in a lower metallicity environment. Essentially, 3I, Atlas is a chemical time capsule providing a snapshot of a galaxy 7 billion years ago, showing us the molecular building blocks available long before our sun existed. Each molecule, each ratio, tells a story not only of the comet's origin, but of the broader history of galactic chemistry and planetary system formation. The broader implications are profound. Interstellar objects like 3I, Atlas are likely passing through our solar system all the time, carrying prebiotic molecules capable of seeding chemistry on planets. While we cannot confirm that these molecules initiated life anywhere, we now know the mechanism is real. Chemical building blocks can survive interstellar travel, remain intact, and enter planetary environments. Early Earth may have received similar deliveries, blending local and interstellar prebiotic chemistry into the conditions that eventually led to life. The process isn't hypothetical anymore. It has been observed, measured, and confirmed across multiple independent instruments. ALMA, SPHEREX, Webb, SWIFT, and MEERKAT all converged on the same conclusion. Avi Loeb's metaphor of 3I, Atlas, as a friendly interstellar gardener, captures this perfectly. The comet is not sowing life, but it is scattering the ingredients, seeds of molecular complexity that can grow under the right conditions. The difference matters. Life requires an environment. Molecules alone do not create life spontaneously, but these molecules are real, abundant, and chemically active, having survived billions of years in the cold void of interstellar space. Methanol, hydrogen cyanide, and the rest form a toolkit that, in the right planetary context, could set the stage for life's emergence. 3I. Atlas has delivered this toolkit to our solar system, leaving behind invaluable data about what other planetary systems are made of. In the end, 3I, Atlas reminds us that the universe is not uniform. Planetary systems vary, molecular abundances vary, and prebiotic chemistry is widespread. Its legacy is the knowledge that chemical complexity is not limited to our solar system, that the molecular seeds for life are floating through the galaxy, and that we have now witnessed one such delivery in action. The comet may be leaving, but what it carried here, the chemistry, the insights, the evidence remains. If you found this journey as mind-blowing as we did, subscribe to stay updated as new data comes in from the Jupiter flyby next week. Share this with someone who hasn't heard about these molecular discoveries and drop a comment telling us which molecule in 3I Atlas you find the most significant. The gardener is almost gone, but it's